Good evening, everyone. Am I audible? Can please someone confirm? Okay, so we shall start now. Okay, so welcome to this live session of NPTEL course named Digital Electronic Circuits. So I'll be assisting you in solving some tutorial problems, which will be similar to the previous year assignments. So this will help you in solving the assignments that will be given to you this year. So I'll introduce briefly. I'm Anand Sigal and I'm a PhD student currently pursuing from IIT Jodhpur, and I'll be again solving few of the tutorial problems that you will be having. So this is the live session 2. You might already had one of the session yesterday by I guess Musfiq. So I have some different questions. So I'll try to cover some different topics. So this is the course outline. Uh, so this is the week one. So yesterday Musfiq covered most of the questions which were related to TTL. So I'll try not to cover from that topic, and I'll cover from the other topics that are in this week one content. So I'll start with some basic questions. So uh, here you can see. So the first question is if log to the base to 512 is x, then what is the value of x? So first of all, why are we even studying this? Okay, sorry for the glitch. Uh, so you know that we are studying a digital electronics course. So we are going from analog to digital circuits. So digital bits, they are 0 and 1. So that is why we need to cover different radix. You might have heard of this term earlier also, where the bases are different and we go from different number system domains. So this is why we need some basic mathematics knowledge also. So that is why we'll need to cover some of the basic logarithm formulas that will have. So as you can see in this question, we have been given that uh, log to the base to 512 is x. So here I can see log to the base to 512 is x. So some of the basics formula that we need to cover from the logarithmic formula are log to the base a if this is to the power b. So it is nothing but b log base a to the to log a. So if this base and this inside value is same, then this constitutes to a value of 1. So this will just convert to b. So this question is similar and the concept that we'll use is similar. So here you can see log to the base 2 and 512 we know it is 2 to the power 9. So it is x. So from the formula that we have just worked out, that is log a to the power x is nothing but x log a. So from this we can easily write this term as 9 log to the base 2 and it is 2. So here we can see the base and the inside term is same. So it is nothing but 1. So we can write 9 into 1 and it get converted to 9. So for this answer, the correct answer is D. If someone has any doubt, please raise your hand and please avoid opening your microphones and camera in the between. You can chat and you can raise your hand if you have any doubts. Is anyone having any doubt in this question? Please confirm by typing it on the chat box. Okay. So one of the number system question that we will cover. So here you can see that it is given 125 to the base r is 203 to the base 5. So the question is basically asking about the value of radix r. So how will you cover this question? So first of all, I'll tell you what is this radix. So radix is nothing but the base of the system or the number system that we use. So some of the fundamental knowledge that you need to have of this R is this R value cannot be greater than the value present inside the variable. So as you can see, I'll give you some examples. So this, let's suppose 125 to the base 6. So 6 is greater than all these integers. So it is possible that we can have this. But once we have 127, let's suppose. So 127 is nothing but it is violating this radix principle. So we need to have this base value greater than the integers which are present inside. This even cannot be 6. So this is some of the fundamentals that we need to know, and the basic concept of solving this radix is this is nothing but if we convert this 125 to the base r, it is nothing but 1 to the power r square into plus 2 to the power 1 and plus 5 into r to the power 0. So it will convert to r square plus 2r1 plus 5, and solving the RHS on the similar manner, it is 3 to the base 5, it is 2 into 5 square, the middle term is 0, and then 3 into 5 to the power 0. So after solving it will get to 53. So once we'll equate both of these equation, we'll get r square plus 2r minus 48 is equals to 0. So now applying basic fraction, so it is nothing but 8r minus 6r minus 48 is equals to 0. So factorizing this, we'll get r minus 6 equals to 0. So we get two possible values of r, minus 8 and plus 6. So we know this number system cannot be in the negative. So the correct answer to this question is plus 6, which is D. Is anyone having any doubt in this question? Please confirm. I shall wait for 2 minutes. Okay, so someone saying repeat. Which question? The last one. Subu, can you please confirm which question are you talking about? Okay, so again I'll say, so this 125 to the radix r, did you get it that it is nothing but r square plus 2 into r to the power 1 plus 5 into r to the power 0? Did you get this part? So yeah, so it is nothing but it is equals to 2 into 5 square. Since the base is 5, so we'll take 5 into 5 to the power 2, and then middle term is 0, so it is basically plus 0 into 5 to the power 1, and then plus 3 into 5 to the power 0, which is nothing but 3. So 25 into 2, 50, and plus 3. So these both equation I have equated and just solved them. So still, is there any problem? Yeah, I'll solve the devices question further. So there are few basic questions, and I'll go to the circuit questions. Okay, fine, I shall proceed. So one of the other basic question here, it says when the transistor are used in digital circuits, so they usually operate in which region? So we know in digital circuit what we want the transistor to work as a switch, since we have just 0 and 1 bit, and we want either 0 or 1. So we know as a switch either this transistor should remain on or off. So there are few conditions that I'll talk about. We know that when a transistor is in cutoff region, this implies this transistor acts as an open circuit. So this is nothing but a open switch. And then when this transistor is in saturation, we know it acts as a short circuit. I'm talking about ideal transistor right now. I'm not even talking about MOSFETs. I'm just talking about general transistor. So it acts as a closed switch. So these are the two regions that we are interested in. We are not interested in the linear region, since linear region the transistor act as a resistor, and in digital circuit we don't want any resistance to come in the circuit. So that is why the correct answer to this question is saturation in cutoff region, which is option C. I guess this is quite basic, so we can move. Shall I proceed? Okay. So again, one more basic question to get you familiarized with the N-channel MOSFET. So here you can see it is given that a n-channel MOSFET has a source, drain, and you might know this term from your electronic devices circuit course. So here you can see this is the drain terminal, this is the source terminal, this is the gate, and the fourth is the threshold respectively. So threshold voltage is nothing but when the transistor get turned on. So this value, if I plot the IDVG characteristics, so this value is nothing but the threshold voltage. So for transistor, there are few basic condition, and I'm talking about NMOS, not PMOS. So for NMOS, few basic condition are when VGS is less than VT. So the transistor does not conduct. So this is basically subthreshold region. So in subthreshold region, there is no conduction. There is only leakage current present in the device. And next is the linear region. In linear region, what we have is first we apply a gate voltage which is greater than the threshold voltage, and we applied a drain to source voltage which is less than this difference. So here the transistor acts as a resistor. And third is the saturation region, where the initial condition remains same, and this VDS now is greater than this difference of VGS minus VT. So here the transistor acts as a short circuit, we can say. It allows the current to pass through it. So in the question, it has been asked that the MOSFET is said to be working in the linear region. So the correct answer to this question is option B. Is it fine? Shall I proceed? You can ask any doubts if you have. Okay, am I not audible enough? Is it better? Hello? Yeah, you are fine. Okay, so I shall proceed. Someone has opened the microphone. Please turn it off. Kiran, can you please turn your... Kiran, can you hear me? Yeah. Okay. So now one of the more basic concept of devices circuit, it is related to temperature rise. So we know as a device engineers, we are interested in this temperature range also. So one of the basic concept is for every 10-degree rise in temperature, there is some reverse saturation current involved in the diode. So it gets changed due to the this variation in temperature. So for this, we need to have some basic idea of the diode equation. So I'll familiarize you with the diode equation. So you might have seen this IV curve for diode in your digital electronic devices course. So this is nothing but the IV curve of a diode, and this is the reverse saturation current that is present in this reverse bias domain. So the basic equation involved in this diode is I is equals to Is e to the power Vt, which is the applied voltage, upon sigma. Okay, we can write this as Va upon sigma Vt and minus 1. So this is the basic diode equation, and this saturation current is given by AQ Ni square, where A is the area, Q is the charge, Ni square is nothing but the intrinsic area concentration, dP upon Lp Nd. This is the diffusion constant and the diffusion length, and this is the donor ion concentration. So similarly, this is Dn upon Ln Na. So here we can see this Is is directly proportional to Ni square. And if I talk about Ni square, it is nothing but NCNV e to the power minus Eg upon Kt. So here you can see higher the this term Eg upon Kt, lower will be the concentration or the Ni value. So here we can see on increasing the temperature, what is happening? We'll have a lesser reverse saturation current. So the relation, final relation comes out to be this Is1 is nothing but the previous reverse saturation current into 2 to the power T2 minus T1 by 10. And this is the temperature difference. So for every 10-degree rise, the newer saturation current, it will be twice. The previous saturation current will be twice of the newer saturation current. So the correct answer to this question is twice, which is option B. Shall I proceed? Okay. So now this is again one of the basic question, that which gates are the universal gates. So universal gates are nothing but, using this universal gate we can make any logic out of them. So maybe I can give you example. So from NAND and NOR we can make this universal gate. So I'll try to make an OR gate using this NAND. So OR gate is nothing but the relation is A plus B, and it is denoted by something like this. So what if we make it out of a NAND gate? Let me try. So we know a NAND gate, a simple NAND gate, if I apply the same output, it will act as an inverter. So here we'll get A bar, and here we'll be getting B bar. And if we apply this operation now again to a same NAND gate, so it will be nothing but A bar into B bar whole bar. So using De Morgan's theorem, we can write this as A bar bar plus B bar bar. So the twice the bar, it will get converted to A plus B, which is nothing but OR gate. And if we apply a NAND gate in front of an AND gate, it will convert to a AND gate. So that is why this NAND and NOR are the universal gate, because we can build any logic out of them. So the correct answer to this question is NAND gate and NOR gate, which is option B. Uh, is anyone having any doubts? Yeah, this PDF will get shared to you. Shall I proceed? Okay, I'll proceed. So again, this is one of the basic circuit question that we will do. So the question says that which logic relation is implemented in the figure shown below. Consider ABC as the input with high state as 5 volt and low state as 0 volt, and Y is the output. So we'll consider few cases to make this question work. So let's suppose we have a 0 at 0 volt and we have a 1 at 5 volt. And suppose we are taking initially all the voltage as 0. And here it is mentioned the diodes are ideal, which means if I talk about D1, if it is forward bias, then it will act as a pure short circuit. There will be no resistance or no voltage drop across it. And if I reverse bias this diode, it will act as an open circuit. So considering this 0 volt applied across all the diodes, we know that this is the negative terminal. So the lesser voltage is applied at the negative terminal, and the positive terminal is at the higher voltage. So all these diodes will be in the forward bias. So what will it will do? It will connect this output Y to the ground. So if either of this A, B, and C gets 0, what will happen? This Y will get converted to 0. So if we basically make a truth table out of it, it will look. So all these cases have a some 0. So this value will get to 0, and the only case that we have left with is this 111. So if we apply 111 to all these input terminals, not 1 volt, it is 5 volt. So here we can clearly see there will be some drop across this resistance, and this diode now will be in reverse bias. So all of these diode will be now act as open circuit. So the final circuit that we'll be having is nothing but this. I'll try to make this resistance and nothing but this Y. So we can see now this Y is high, which is 1. So this is the basic condition of an AND gate. You can see if all the inputs are 1, then only we are getting the output as 1. So the correct answer to this question is AND, which is option C. Is anybody having any doubt in this question? Okay, I'm assuming that you don't have any doubts. So I'll proceed in a minute or so. Okay, so I'll proceed now. So this is again a diode question. So in this circuit, you can see there are four diodes named D1, D2, D3, and D4, and it has been asked that in which of the state will the current flow through this resistor R. So we can see the only closed path that we can have so that this resistor, the current can flow through this resistor R is this. It will look something like this. So for that, we need to know the basics of diode that we have already studied, that for an ideal diode, if it is forward biased, so it will act as a short circuit, and if it is an if it is reverse biased, so it will act as a open circuit. So to make it work, we need to turn off this diode D2 and D4 to make this closed loop. So let me try to make a circuit out of it. Again, the diodes are ideal. It has been mentioned that the diodes are ideal. So if I try to make this circuit, it will look, it is a closed circuit now. This is a resistor. This is an open circuit. This is again open, and this is closed. Yeah. So here you can see there is a closed path. So this will be the condition when the current will be getting passing through this resistor R. So let's check the options. So this D1 and D3 needs to be remain on. So D1 on, D1 on, D3 on. Okay, so the correct answer to this question is option C. You can see D1 is on, D3 is on, and rest of the diodes are off. Any doubts in this question? Okay, I'll proceed. Okay, so there is a concept of noise margin in this week's one course content. So we'll try to cover it. So the basics of noise margin is there are four voltages involved in the inverter, which are nothing but the first is the minimum guaranteed output high voltage that we'll get. So it is named as VOH. So the question says that the minimum guaranteed output voltage is 4 volts. Then the question says minimum accepted input high voltage, which is nothing but input high voltage VIH, which is 2.8 volt. The next part given is maximum guaranteed output low voltage, which is VOL. So it is given as 1.2 volt, and the maximum accepted input low voltage, it is nothing but 1.8 volt. So we need to calculate the overall noise margin of the logic family. So noise margin is nothing but the difference for high, the difference of output high minus input high voltage. So we can see in the question both of the values are given, 4 minus 2.8. So it will give a value of 1.2 volt. And if we try to calculate the noise margin for the L case, then it will be VOL minus VIL. Sorry, it will be VIL minus VOL. So it will be nothing but 1.8 minus 1.2 volt. So it is nothing but 0.6 volt. Now the overall noise margin will be the minimum of this both high and low. Since we need a good noise margin, so we'll take the minimum, the worst case out of them. So the overall noise margin will be nothing but the minimum of noise margin high and noise margin low, which is nothing but zero point 0.6. So the correct answer to this question is 0.6, which is option A. Okay, so which question are you trying? Ashwini, can you please say which question are you on slide number? You can see the slide number, right? So can you write the slide number which I need to repeat? Okay, 10. Okay, this question. So this question says that we need to have a path by which the current will flow through this resistor R. So you can see it is only possible. Let me try to change the color. So it is only possible via this. You can see this wire, this green color. So if this diode is forward biased, then the current will go through this. And then if this diode is reverse biased, forward biased again, we are neglecting this part because we are reverse biasing this circuit. So now the closed loop will be like R, and then D3 will be again forward bias. This D4 will be open circuit, which is reverse bias, and we'll have this closed loop. Did you get this part? This loop? Okay, so that is why we are making this D1 and D3 as forward bias, so which is the option C. Is it fine now? Yeah, no problem. Okay, so yeah, again one of the theoretical question. It says that which of the following statements are true about CMOS logic. So we know basics of CMOS. So we know a CMOS has a very high input impedance and it has a very low output impedance. And since it is a CMOS, it only dissipates dynamically. There is no static power dissipation. So let's try to get through the options. So first option says that CMOS has a very high input resistance and hence draw a very low current. So this is correct. Okay, so the next part says that CMOS has a high fan out as compared to TTL. So a lot of TTL questions were covered in the yesterday's lecture. So this is also true that CMOS tends to get a fan out of approximately in the range of 50, whereas this TTL only has this fan out of 10. So this is the maximum number of gates that can be driven through this TTL. So this option is also correct. But when it comes to the speed, then we can say this TTL is faster than CMOS. So why is it so? Because this CMOS has a less current drive capability. So less current drive capability means the rise time and the fall time is slower in this CMOS case as compared to TTL. So that is why for the same biases, TTL is considered faster than the CMOS. So this third statement is not true. Again, yeah, CMOS has a very low packing density. We know in uh, less space it can cover quite large number of CMOS circuit, and as compared to TTL, since it is BJT based, so yeah, obviously BJT will take more areas compared to the CMOS logic circuits. So this is also correct, and yeah, it has a lower power dissipation since there is no static power dissipation in this circuit. So considering was first, second, fourth, fifth are sorry, first, second, fourth, fifth are correct. Okay, this CMOS has a low packet density, it has been written. So no, CMOS has a high packet density. Sorry. So since for a smaller area, it can have a large amount of chips. So please be attentive. So I said that CMOS has a low packet density. It is not true. CMOS has a high packet density. So this option is also wrong. Only first, second, and fifth are correct. So the correct answer to this question is option C. Is there any doubt in this question? Okay. Let me try to proceed. Shall I proceed? Okay, so this is a basic circuitry question. This is a CMOS logic based circuit which contains a circuit for PMOS and NMOS. So these are nothing but a dual of each other. So I'll try to explain it taking all the possible cases that how can we find the output expression using a given circuit. So for that, we'll take all the possible cases. So first we'll take when this C is off. You can see this is a NMOS. So if we apply a low voltage out of it, this NMOS will be in cutoff region. So there will be no connections here. And for a PMOS, it will be in saturation. So this high voltage is directly through this Y. So you can see once we get a C0, we'll always get a output 1. Is there any doubt in this part? Please respond if there is no doubt. Okay. So now similarly for the case of this A and B. So if we make both of them as 0, so here you can see if both of them are 0, then there will be no connection between the ground and this output terminal, and these both PMOS will be in saturation. So again, if both A and B are 0, so what will happen is Y will get high. So these are some of the cases. So if I try to make the truth table, so we can see when C is 0, these all will get 1. And when both A and B are 1, which is this case, this will get 1. So now we'll check for the remaining cases when either of them. Here you can see when A is 0, so this will be cut off, and then B is 1 and C is 1. So there will be a path across the ground. So this will get 0. And again, the same with this. C is 1 and this A is 1. So there will be a path across the ground. Same with this. So we can solve it either using K-map, which will be taught to you in the upcoming sessions. So the basic, we can minimize this Boolean expression, and there is a shortcut also we can, from which we can solve this type of questions. I'll try to explain this shortcut first. So once you see this CMOS logic, what you can do is you can just look at the NMOS circuit. So wherever this NMOS is connected in series, it is just nothing but a AND. So the shortcut is if NMOS are connected in series, it is an AND operation, and when NMOS are connected in parallel, it is OR operation. So here we can see A and B both are in parallel. So this is nothing but A plus B, and which is in series with this C. So it is A plus B into C. Now the output will be the inverted form of this NMOS, since it is an NMOS. So the final output, if we try to use this shortcut, will be A plus B into C whole bar. Now using De Morgan's, we can write this as A bar into B bar. This dot will get converted to plus C bar. So the correct answer to this question is option A. Uh, if you have any doubts, you can ask. Okay, I'll proceed in a minute. Okay, so next question, it deals with propagation delay. So it will cover some of the concepts of propagation delay. Okay, so we know the basics of propagation delay. It is nothing but it is due to the finite switching speed of the circuit. So we know there is some rise and fall of this input that we apply, the pulse. It is the rise time and this is the fall time. So it is due to the finite capacitance in the circuit and other things, the delay due to transistor. So the propagation delay, the first expression or the first option is basically the direction of the definition of propagation delay, which is it occurs due to the finite switching of speed and the circuit capacitor. So the first option is correct. And if we talk about the propagation delay is directly proportional to power dissipation, so we can do this basic. So if we have a lesser propagation delay, what will happen? The circuit will use high energy, and that will result into inverse relation of power dissipation since the circuit is using high energy. So the option says that it is directly proportional, which is not true for the case. So the second option is not correct. So let's check the third option, which is propagation delay associated with rise time and fall time. Yeah, so this is the basic. So I already told that this is the rise time and this is the fall time. So yeah, it is associated with rise and fall time. So third option is also correct. And if we talk about that propagation delay is quantified by averaging the time taken from high to low and low to high. Yeah. So this is nothing but tau propagation high, sorry, low to high, and this is nothing but tau propagation high to low. So we calculate this propagation delay by taking the average out of them, which is nothing but tau PHL plus tau PLH by 2. So yeah, this propagation delay is quantified by averaging the time taken from high to low and low to high. So this option 4 is also correct. So the correct options are 1, 3 and 4, which is option D. Is anybody having any doubt in this question? Please respond even if you have any query in the previous questions that we have discussed. Let me go through them once. If you'll try to see. So this was a basic logarithmic question, and then there was again a number system question. There were some transistor questions. So if you have any doubt, you can just write the slide number. I'll try to explain it again. Now this is again some basic device question. This was a diode equation. Now universal gates, this is slide number 8. This is the circuit question, which was slide number 9. This is the AND gate circuit. This was the diode question. Again a circuit question. So this is 10. Noise margin, this is 11. And then this CMOS logic is slide 12. And then we calculated the output expression, like going through them one by one, and we got to know a shortcut that how we can solve that directly. I'll repeat that again because it will be useful for you in solving the assignment. So when both NMOS and when the NMOS are in parallel, so what it is nothing but OR logic, and when the NMOS are in series, it is nothing but AND logic. So again, I'm trying to write this is A plus D into C, and the output will be the inverted form of the output that we'll get. And then there are basic De Morgan theorem. You already know that. So again, we discuss a bit about propagation delay. So is anyone having any doubts in this question? If not, then I'll proceed in a minute. Okay, yeah. So one thing you all can do, you can try to solve this question by the shortcut that we used in the last question. It is a similar question, so try to use the shortcut, then I'll try to explain from your end maybe. Is it easy to solve now? Can anyone confirm if they have solved them? Okay, you will get it soon. Like when the week will get over, you will get the recording of all the live sessions all together. There will be 3 live sessions per week. So this is the second one. Okay, someone has answered B is correct. Okay, we'll see if B is correct. Anyone else has any different opinion than Srinivas? All of you are getting an answer B is correct. Okay, someone has written A is correct. Okay, there is a lot of difference in opinion. We have got 3 answers A, B, and C. So, okay, I'll try to solve it and maybe I'll try to explain this again. Maybe this will help. So, the basic of the shortcut was that if somewhere NMOS are in parallel, you just have to write the OR combinations of them. And if NMOS are in series, you just need to write AND combination of them, and then finally just invert the output. So now I'll proceed to the question that we have. So here this is again a CMOS logic, so we'll just look at this section. So here we can see this A and B are nothing but in series. So and this whole is in parallel with this thing. So final answer will contain something like A into B plus the solution of this thing. So now we can see this C and D are in parallel. So what it means, C and D are in parallel means it is nothing but OR logic C plus D and which is in series with E. Is there any doubt in this part? I can solve it by a longer method also by making a truth table, but this since it has a file, it will take a lot of time. So you need to know this shortcut. Kindly tell if anyone is having any doubt in this part. I'll try to explain again maybe because everyone is getting different answers. So when NMOS are connected in series, it is nothing but AND logic. And whenever NMOS are connected in parallel, it is nothing but OR logic. So this is C plus D, which is connected in series with E, and this is A into B. And this AB and C plus D into E are connected in parallel. So this is the first term, this is the second term. And they are connected in parallel, so it will be plus. And the final output is what? The inverted waveform of this. So by checking option, the correct option is option C, not A and B. So whosoever has written A and B, are you clear now? Or do I need to explain it once more? Okay. Again, this is important, so let me try to rub this up. So here you can see, again I'll try to explain once. When both NMOS are in parallel, it will be OR, and when both NMOS are in series, it will be nothing but and the output will be the inverted waveform of this. I guess it is clear now. I've explained it like 3 times now. So yeah, so we shall proceed in 2 minutes. Okay, so let's proceed. So this is again one of the theoretical questions. So it says, let me check. Yeah, maybe we can do an exercise in this because this is an important concept. So what we can do is we can even go back to the circuit if we have this equation. So let's suppose we don't have this circuit now. Maybe I can use this page and we only have this equation, which is C plus D into E plus AB whole bar. So maybe you can get a circuit question like, if you need to implement this logic, how you can implement this using the CMOS logic. So you need not to worry about it. We know that plus means parallel and this dot means series. So we can proceed one by one. Here you can see C plus D are in, if we just talk about the NMOS logic, it will be in parallel, right? And it will be in series with E. So we have got this term which is parallel with, which is in parallel with both A and B. So this is the one of the branch of the NMOS and this is in parallel with A and B. So we have made the NMOS part of the circuit and here we'll get the output after we'll make the PMOS part. So PMOS is nothing but the dual of this NMOS. So whatever is in parallel in NMOS will be in series in PMOS, and whatever is in series in NMOS will be in parallel in PMOS. So let me try to make the circuit. So it will look something. So this C and D will be in series and this A and B will be in parallel. First of all, we'll make this A and B. A and B will be in parallel and they will be in series with this term. So again C and D will be in series since it is a PMOS, and then it is in parallel with E. So once we connect this to here, I hope you get it. I don't have enough space, so I'm writing it here, and once you apply the VDD here, so this will be the final circuit that you will be getting from the question. So this is the same circuit as you can see. So you can solve both the ways. Either from circuit you can get the equation, and from equation you can even make the circuit out of it. So is there any doubt in this? Okay. So I'll proceed in 2 minutes. So the rest of the questions are purely circuit based. So I'll give you a brief about whatever has been discussed. So first we discuss few mathematics problem that we need to know few relations and all. The number system we discussed a question and then few device problems, that what is the region that we should look out uh, for a device using our digital circuits. So we should be clear that we are dealing digital circuits as switches, so we need it as open or closed switch. So we do it in cutoff and saturation. Then we talked about this basic condition that MOSFET works in a linear region when this drain to source voltage is less than the difference in the gate to source voltage to the threshold voltage. And then a basic concept of the temperature. So this is also quite important. For 10-degree rise in the temperature, change in the reverse saturation current is twice from the previous part. So we discussed here that this current is nothing but reverse saturation current into this exponential equation, which it looks like. So, and this reverse saturation current is dependent upon the intrinsic carrier concentration, which is Ni, and even the square of it. So again, we know the relation of Ni square, which is related to this exponential term of Eg upon kT, where T is the temperature. So higher the value of this uh, power, so lower will be the concentration, and lower will be the concentration, lower will be the reverse saturation current. And on solving, we get this uh, relation that IS1, which is the newer saturation current, is dependent upon the last saturation current if we apply a different temperature to this factor of 2 to the power T2 minus T1 upon 10, where T2 is the uh, T1 is the initial temperature and T2 is the temperature which has been applied, which has been increased to T2. So the difference will be, if we take this difference as 10, so IS1 will be nothing but twice of IS0. So that is why we got here twice. Then again, this is basic universal gates. Maybe you can at home you can try to make XOR and XNOR out of these NAND gates. These are like the basic question. Even in gate they ask that what is the minimum number of NAND gates required to make XOR gate, XNOR gate, because these are some important questions. So at home you can try to make XOR gate using NAND, or maybe XNOR gate using NOR gate. It is possible and it is quite easy. So once you'll get the idea, it is quite possible to do it. Okay, for this maybe I can give you a hint. So XOR is nothing but this A B bar plus A bar B. You might be aware of it. So let's have this. Let's have a discussion on this. Okay, maybe I need to rub somewhere. You can also try with me as I'm doing. So let's suppose we have been given a relation which is something like AB plus CD. Let's suppose we have this. So since we know that these are the universal gate, NAND gate and NOR gate, so can we try this making, can we try to make this relation AB plus CD using just NAND gate? So this is the question now. Since it is something important, so using the basic AND gates and OR gate, it will look something like this: AB and then CD and then OR. So it is AB plus CD. Okay. So now we have to make something out of it so that we can get these all as only NAND gates. So there is a shortcut where uh, what we say is NAND is easy to implement when there is some AND or implementation. So it is a concept which is known as AND or implementation. So in this circuit you can see there is AND first and then OR. So if I try to make some different color, so this is AND implementation, this is again and this is OR. So there are two phases in this circuit. This is the and this is OR. So once we get this AND or implementation, it is quite easy to do it using NAND gates. It is not as easy to do the same using NOR gate, but now we can use NAND gate to make this circuit quite easily. So NAND and AND or implementation are like uh, what we can say friends to each other. So how is it possible? There is a shortcut AB. So this was the circuit. So what we will do is leave some space, and this was the OR gate. So what we need to do in this is just bubble them out. Bubble them out means just invert the logic. So we know this is now has become n, this has now become n, and this bubble will get nullified by this. So this is nothing but adding two inverters in the wire. So this is nothing and it will remain same. And again this bubble will get cancelled by this. Is there any problem in this? Can you tell? If there is any doubt, please ask now only. Please respond. Else I'll continue in a minute. Okay. So since there is no query, so we can see that these two NOT gates are cancelling each other. So now this is nothing but NAND gate, this is a NAND gate, and we can check this logic now. So this is OR which has been connected by NOR. So if there is A, there is B. So the output of the circuit will be A bar plus B bar. And from a NAND gate, this is a NAND gate. If you apply AB, so what we get is A dot B whole bar, which is nothing but using De Morgan's A bar plus B bar. So this circuit and this circuit are same. So what we can do, we can replace this by NAND gate, right? So let me try to remake this somewhere else. Maybe here. Yeah. Okay. Yeah. So AB, CD, and then this. So this is now three NAND gates, and now the logic has been converted to AB plus CD. So this is how we can convert any logic to using this NAND and NOR implementation. If it has been this, let's suppose A plus B into C plus D. So this is will be this. Okay. So this thing will be nothing but OR and implementation. So maybe you can try at home. This is A plus B, AB, this is CD, and this is AND. So this is nothing but OR and this is nothing but AND. So try to make this using NOR implementation at home. You need not to do anything, you just need to bubble them and try to check the logic. It will be very easy. So this is how we can make any logic using the NAND NOR gates. Is it fine? We shall wait for a minute. If anyone is having any query, they can type in the chat box. Even if you don't have any query, you can write that you don't have any query. Okay. Okay. Let me proceed then. Okay, it got. Okay, let me wrap this up. Yeah. So again, this was a basic AND gate. We have already covered it. This was a question. So someone was having any doubt in this. So this is also a basic question. We need to just turn them off and turn this on. So these on. Noise margin. This is a basic concept. You already know something like this. VI. This is VOL, VIL, VOH, VIH. This is NMH. This is NML. And we get the minimum out of the out because we need to take the worst case. Then some facts about CMOS, that it has a very high input impedance, low output impedance. It has only dynamic power dissipation, no static power dissipation. So it also has a high packet density. We can integrate more CMOS in a lesser area. Then it is not generally faster than TTL because of its less current drive capability. But yeah, CMOS is better than TTL. Yeah. Then we studied this concept of getting the equation out of these circuits. Then some facts about propagation delay. It is nothing but due to the rise and fall of the circuit, and it occurs due to the finite switching time and the capacitance present in the circuit, because capacitance is nothing but the time constant is RC. So if there will be a constant capacitance, then there will be some time delay. Again, we need to average the low to high and high to low to get the final propagation delay. Then again a similar question, and what we did is from the equation we tried to make the circuit out of it, and we were successful. I hope you all got it right. So no one is, if no one is having any query, they can tell so that we can proceed now. Please respond. Okay, yeah, the recordings will be shared to you when this week will end. Okay, shall I proceed then? Fine. Okay, so these are some diode questions. So what we did above is more quantitative analysis. Sorry, the qualitative analysis. There were no like the biases involved and the values of resistance involved. So there will be few quantitative questions now, which will make your concept stronger in case of diodes and also a BJT. So you can see this circuit, and what it says is we need to determine the V naught of the given network. And we have applied, there is a diode, and these are not ideal diodes, so these are silicon diodes. Okay, so let me try to cover what is silicon. What I mean by silicon is once they will be in forward bias, there will be a specific voltage drop across them. So in forward bias, they will act as a voltage source, and the voltage source is the drop across silicon, which is generally 0.7 volt. And in reverse bias, they will act as an open circuit only. So there are few cases. So ideal one was it is act as a short circuit, and it acts as the open circuit. Forward bias, reverse bias. This was the ideal one. This is though a bit practical. There will be some drop, and again this will be reverse bias. And there are more cases also when we take the internal resistance, which is something RR and VD. So this is the most practical case that we take when we change this diode. Here what we are taking is we are taking that there will be a certain voltage drop across this diode. So these are the three cases. Is there any doubt in this? Please respond. Okay, what is the doubt? Okay, I need to repeat. Fine, I'll repeat. Let me. Yeah. So what we were doing in the above questions, all the questions mentioned that the diodes are ideal. Ideal means that in forward bias, what will happen? The diode will act as a short circuit. It will just let the current pass through it. There will be no voltage drop, and in the reverse side, it will act as an open circuit. That it won't allow any current to pass through it. So this is what is the ideal case. So if there was a diode here, so it will be get replaced by short circuit, and this will get replaced by open circuit. So this is what we read in the previous question, because all the questions said that iode assume that the diodes are ideal. So now if I talk about a more practical case, which is this question. So what it has silicon diode. So what we will assume that it will have a voltage drop across it, which is VT. And in the reverse case, it will be open circuit only. So this is the second case that we'll consider in this question, that there will be a drop across the diode. And the third and the most practical case is when we take the internal resistance also, which is R, which has some value and a voltage drop. So this diode is nothing but V equals to VD plus some IRR. And reverse bias is again this open circuit. So these are the three cases for diode. We were talking about the ideal case in the above questions, and now we'll talk about this case, in which there will be a significant voltage drop across the diode when we go in forward and reverse bias. So is it clear now? Please respond whosoever had the doubt. Is it clear? Okay. So now what we'll do? We can see this diode, the applied voltage for the diode D1 is quite high, which is 10 volt. And we can see this diode is connected to a ground, which is 0 volt. So we can assume few things seeing just the figure, that there is a huge possibility that this diode D1 will be in the forward bias and this diode D2 will be in the reverse bias, since the positive terminal of this diode is connected to a very high voltage as compared to a negative terminal, and for the D2 the positive terminal is connected to ground. So there is no possibility of it getting forward bias unless this V0 will be in some negative value. So seeing the question, we'll assume that D1 is in forward bias and D2 is in reverse bias. And we'll prove that this assumption of ours was correct, or we if it. Can you repeat the equation? Which equation are you talking about? Uh, okay, this question. Okay, okay, yeah, I get it. I guess you might be talking about this. So it was nothing. I was just saying that a whole diode is nothing. There will be some resistance, so there is some current. So the whole equation, the total voltage drop across the diode will the it is due to the silicon drop, which is Vd plus whatever the current into the resistance. It since we have also mentioned there is some series resistance which is making the drop across the diode more. We can write this as Vd naught and we can write this as Vd if it is confusing. So yeah. So we have assumed that our diode D1 is in forward biased and D2 is in reverse biased. So now we'll replace D1 with a voltage source which is Vd, and we'll take 0.7 volt because it is a silicon diode. So let me try to remake the circuit. Here it is 10 volts. Here there will be a voltage source which is 0.7. Then this diode is in reverse bias. So we'll open circuit it. Then there is V0 and then there is 1 kilo ohm resistor, and here again the ground. So we can see this circuit can be neglected, and V0 will be nothing but whatever the current getting passing through this circuit. So V0 will be nothing but I into this 1 kilo ohm. So we can apply KCL here, sorry KVL here, the Kirchhoff's voltage law. Since this loop is complete, so we can write this as minus 10 is the voltage plus 0.7 and the current across the resistance and the resistance value which is 1 kilo ohm, and it is 0. Is anyone having any doubt in this equation? I hope you do know about Kirchhoff's voltage law. Okay, so you know. Again, I'll try to explain. So this is the voltage. We can also write in some other way that this is plus 10 volt, and then there will be a drop of minus 7. And since the current is in this direction, so yeah, this is the alternate way of writing this. But this is more simplistic. I hope you get it from this equation better than this. So if I try to solve it, it is nothing but minus 9.3 plus I into 1 kilo ohm. So now this I is 9.3 upon 1 kilo ohm. It will give a current of 9.3 milliampere. Is there any doubt here? Okay, I'll proceed. So V naught is nothing we talked about. V naught is nothing but I into this 1 kilo ohm resistor. So we get the I as 9.3 milli to 1 kilo ohm. So milli and kilo will get cancelled since it is 10 to the minus 3 into 10 to the plus 3. And we get the final V naught as 9.3 volts. So the answer to this question is 9.3 volts. If anybody is having any doubt, they can ask. Okay, fine. We'll proceed. So there is something similar, but the question asks for the determining the output level of the positive logic AND gate. So we have studied that this is an AND gate. There was a question which was similar to this, and now the question is asking about some quantitatively. So here we can see that there is some voltage applied across D1 and there is ground across this D2, and this resistance is 1 kilo ohm, and even here there is some voltage applied. So yeah, in the previous question also, yeah, we assumed that this diode is in forward bias and this is in reverse bias. So our assumptions were correct because this current is coming out to be positive. Since we assume that this is forward bias, so there should be a current in this direction only. So since this is coming positive, so our assumptions were correct that the diode D1 is forward biased and this D2 is reverse biased. If the assumption was wrong, then this current would have been coming in some negative value, which would have proven that we have assumed wrong and we need to take some different case. Yeah, this is one more thing that I need to add. Same with this question. So we'll assume from looking at the circuit, so we can see here the negative terminal of D1 has quite a high voltage as compared to the positive terminal, or a higher voltage, because here is also a 10 volt, but we will assume that D1 is in off state or reverse biased. And here you can see that this D2, the negative terminal, is connected to ground and the positive is having some voltage, so we will assume that D2 is in on state and it is forward biased. So once we say on state, that means that the current will be something like this, in this direction, something like this. If this current in this direction comes positive, then our assumption will be correct. So let's try to make a circuit out of it. So we are saying that D1 is in off state and D2 is in on state. So it is nothing but open circuit. Again, these are silicon diodes, it is written. So we'll take the voltage drop model. So this is reverse bias, 10 volt. Then this is forward bias. So I'll take a voltage like this, which is VD. Again, there is a resistance R, which is 1 kilo ohm. There is a 10 volt here, and there is a ground here since it is 0 volt. Is there any doubt in this circuit? I hope it is clear. Is there any doubt? So now we can see that we have taken the assumption that D1 is in forward bias, so the current will be something like this, in this direction, anti-clockwise basically. So we'll try to solve it. Again, we are applying the KCL, so it is, we can write minus 10 plus I into R, which is 1 kilo ohm. I'll write minus 10 plus I into R plus VD equals to 0. So this is minus 10 plus I into 1 kilo ohm and plus VD, which is 0.7, equals to 0. I hope this is clear. So we'll try to solve. This is minus, let me take some space, maybe here. Yeah. So on solving, we'll get minus 9.3 plus I into 1 kilo ohm is equals to 0. Here we'll get I as again 9.3 milliampere. You can solve that. Now what we need to do is we need to get the voltage level V0, the output level, yeah, for the positive logic AND gate. So V0 is again nothing but, since the current is something like this, we'll write minus 10 plus I into sorry, V naught is here, this voltage. So it will be minus IR plus 10 volt. I hope there is no confusion in this equation. Is there any confusion in this equation that V naught is minus I into R plus 10 volt? Please respond if there is any doubt. So we have all the values. I'll just substitute the values, which is 9.3 milli into 1k. So million kilo will get cancelled, and it is nothing but minus 9.3 plus 10. So the output level for this positive circuit AND gate will be 0.7 volt. So what we thought that it will be 0, but the lower voltage is 0.7, not 0. So from this we can surely say that the diode D1 will be in offset, that is, it was reverse bias, and D2 was forward bias, since our current was coming positive. So our assumption was correct. So the state of diode is therefore confirmed, and this 0.7 for V0 is enough or sufficiently small to be considered at the 0 level. So what I'm trying to say is 0, even 0.7 volt will say that the diode is at 0 level. I hope we took 10, that is even value, right? No, that is not, this is E value. Okay, let me try. Wait. Let me try to explain here. This is the KCL. So you can see when this is forward bias, so this is nothing but a voltage source of 0.7. So here we are applying KCL. That is not E1. This is E. Here I have written minus 10. Minus 10, then plus I into 1 kilo plus VD equals to 0, and this VD is 0.7. So it has come minus 10 plus 0.7 plus I into 1 kilo ohm equals to 0. From this I comes out to be 9.3 milli. We can say that we are measuring voltage across diode T2. Yeah, so we are assuming, first of all, if this has not been in the offset, so there will be some other diode equation. So yeah, V naught is nothing but the equation, the drop across the diode in this case, we can say. Yes, you are correct. But we need to assume both, all the cases, that when D1 and D2, there might be a possibility that this can be on instead of off. Is there any doubt in this question? Ashwani, I hope your doubt is clear. This E1 is not taken in this equation. This E is taken in this KVL equation. Is there any doubt? If E is less than 12.7 volt, then D1. You are saying if E is less than minus 12.7. So we are not sure. We need to check. It is not like there will be some current across it. So we cannot say surely that if it is. First of all, why you write minus 12.7? This is E. This is 0.7. If even the drop is 0.7, so it will be 0.7. You have written minus 12.7. Yeah, 10.7. If this voltage have been greater, so we might have assumed that this is on or something like that. Yeah, we can say that if this is 10 and this is there would have been this 0.7 or maybe a higher voltage, maybe 12 volt. So that might say that this diode might have been in the on state. I hope this confusion is clear. Can you explain the equation V naught? Okay, V naught equals to minus IR plus 10 volt. Yeah, this one. Okay, fine. So V naught is nothing but the voltage across this. Here you can see this is V naught, this is ground. So the voltage across this will be V naught. Let me try. So yeah. So V naught is nothing but the drop across this resistance and this plus 10 volt. So V naught will be something plus 10 volt. And we know the current is in this direction for this case. I hope you get it. So since it is in the reverse direction, so I'm taking minus I into R. Is it clear? So this is minus 9.3 into 1 kilo, which is minus 9.3 plus 10. So that is why this V naught is coming out to be 0.7 volt. Is it clear, Ashwani? Okay. Is anyone else having any doubt? If you are not having any doubt, please respond once so that we can proceed. So these two are important questions from the quantitative perspective. So I'll give a brief of them again, like quite fast. So you can see what we have done is in this question we have a direct 10 volt applied to this D1 and a ground applied to this D2. So we assume that D1 is in forward bias and this D2 is in reverse bias. And now we needed to check that if our assumption is correct or not. So we made the circuit out of it. Since it was a silicon diode, we take a voltage drop VD, and for the reverse bias, we take a open circuit. So after applying KCL, what we got is minus 10 plus 0.7 and then plus this resistance into plus current into this resistance is 0. So this was the equation, and after solving this, we got a positive current, which proved what it proved that our assumptions were correct, that this diode is in forward bias and this diode D2 is in reverse biased. And once our assumption was correct, we just needed to calculate V naught, which was nothing but the voltage across it. So it is similar to this question. So here also you can see this V naught is nothing but, since the current is in this direction, so this is plus I into resistance. That is why we got 9.3 as the answer of this question. So, so the answer to this question is 0.7 volts. Yeah, Avinash, you have any doubt? You can say, or if you have any doubt, you raise your hand. Avinash, are you there? Okay, I am assuming it was by mistake. So yeah, we should proceed. So I'll try to cover up a concept, so it might take time. So this is now a concept which I'll try to cover through a question. So here it is given that according to the given bias condition, prove that this BJT is acting as an inverter. So you might have like read about the basic condition of BJT. So Avinash has responded. So you have any doubt? Okay. So according to the given bias condition, we have to prove that this BJT is acting as an inverter. So this is the BJT that we are, and we have been given certain bias condition. All the resistances value, the HFE of the BJT, the VCC, and the high and the low voltage for this BJT. So we just need to prove that this circuit is acting as an inverter. So we know what is an inverter. Inverter is nothing but a NOT gate. If you are applying 1, we are getting 0, and if you are applying 0, we are getting 1. So you might have seen this circuit also somewhere, CMOS inverter. This is the word we use more often now, VDD. This is the output and this is the input. And this is nothing but something like this. Transfer characteristics look like this. So we'll now try to do it using some BJT. Uh, for that we must know some equations about BJT or the conditions or the regions that BJT has. So let me try to wrap. So for a NPN BJT, first of all, this is an NPN BJT since this arrow is outside. For an NPN BJT, what we can say, it is in cutoff when this voltage between, this is base, this is collector, this is emitter. When this voltage VBE is less than the pinch off voltage, which is 0.6, and this VC is open circuit when it is in cutoff. So there will be no current. This is open circuit. So whatever this V0 is, it will be getting to VCC, and then again this, there will be no collector current or no base current when the NPN transistor is in cutoff. Now the second region is the active region. Active region implies when it is somehow acting like a resistor. So here, when this VB is greater than 0.6 and less than 0.7, 0.6 and 0.7, and this VCE is now also greater than 0.8. And the third condition is the collector current, which will be nothing but the amplified version of HFE of the base current. So in the active region, it will get, the collector current will get amplified by a factor of this HFE. Okay, there is one more region which is left, which is saturation region. So in saturation, now this VB will be even greater than 0.7 volt, and it is less than 0.8 volt, which is VC for the previous case, and now this VC will get reduced to 0.2 volt. So these are the certain conditions that we are talking about. And for saturation, there is a condition that we need to write, which is IB is greater than ICH upon HFE. So in saturation, it will be something like the whole current is passing through this. So these are the three cases: cutoff, active, and saturation. And these are the conditions for saturation. This is for active and this is for cutoff. So now we'll try to solve this question and prove that this BJT is acting as an inverter. Are these conditions clear to all of you? Please respond. So is it clear to all of you till now? Though these are the value for silicon, like this 0.7, 0.6. So these values are standard for only silicon. So we are just taking a particular case just to prove that this circuit works as an inverter for a certain bias condition that we are using. We have been given some values, so we'll use them to prove that a BJT can act as an inverter. These are not standard equations. Yeah, this and this are standard equations. This and this. Okay, so let me try to all of it. Yeah. So the procedure of this question is, first we'll assume that the input voltage applied to this BJT is 0. Oh, sorry, the low voltage given in this question is 0.2. So we'll assume that it is low, which is in this question is 0.2. So when 0.2 is applied across this resistor, so we know that this VBE will be always less than 0.6. We have just read the cases, so transistor will be in cutoff. Which will imply that this is an open circuit. So whole V0 will be now at the VCC, and VCC is given as high voltage, which is 5 volt. So collector emitter current will be 0. Which implies this V0 will be VCC. So we have got something like, when we applied a low voltage, which is 0.2, we are getting an output of 5 volt, which is high. So low to high. One case has been confirmed that if we are giving 0, we are getting a 1. Now we'll check, when we are getting a 1, are we getting a 0 or not? If we are getting a 0, then we can confirm that this circuit is acting as an inverter. So yeah, I'm limited in space, so I'll remove this. Yeah, so now considering that input voltage is nothing but high voltage, which is given as 5 volts. You can see 5 volts is given. So once 5 volt is applied, so we know that this VBE will be greater than 0.6. So now the transistor will not be in cutoff. So what we'll check out now? Can anyone tell what we can check out now? So we'll check for active and saturation now. So we will assume that since it is greater than 0.6, so we'll assume that VB is 0.7 volt. And once VB is 0.7 volt, we can apply a KCL here. VI, we know it is minus, VI is 5 volt plus IB RB. IRB is given as 22 kilo ohms. And then plus VB, which is, we have assumed 0.7, is equals to 0. Is there any doubt in this equation? Minus 5 plus IB RB plus this VBE is equals to 0, since there is no resistance here. So is it fine? So I can write something like 5 minus 0.7 upon 22 kilo ohm. Is it fine? Please confirm. So on solving, it will get something like 0.195 milliampere. Now we get the IB, so now we'll check the maximum current which we can flow through this collector. Maximum collector current, assuming we know that for saturation we need to assume that VB is 0.2 volt. We just wrote it earlier. So it will be nothing but ICS will be VCC minus maximum collector current, means this is in saturation. So maximum collector is VCC minus VCE upon RC. So this is nothing but VCE minus VCE upon RC. There will be a whole current IC here, which is IE only. So now we can write it as 5 minus VCE. VC is nothing but 0.2 that we have assumed. Oh, it is VCE, sorry. And upon RC, which is 1 kilo ohm given in the question. So this will get, I guess, 4.8 milli. So we see here 4.8 milli is a maximum current. So if you remember that for saturation we need to check, there was a condition that this 0.195 milli, which was IB, must be greater than equals to, sorry, ICS upon HFE. So this was a assumption, oh sorry, this was a condition that needs to be fulfilled for that, for this transistor to be in saturation. And if this transistor is in saturation, then this V0 will be low. That will confirm that this BJT is acting as a inverter. So I'm rubbing that. Should I remove all this? Please confirm. Okay. So yeah, we'll check. So this IB was coming out as 0.9195 milliampere, and we just calculated ICS, which was nothing but 4.8 milli, and the HFE is given in the question, which is 50 milli. Sorry, not 50 milli. It is just 50. Okay. 4.8 upon 50. This was milli. So on solving, this will be like 0.096 milliampere. So this is greater than. So this condition is getting satisfied, that this IB is greater than ICS upon HFE, which will confirm that this transistor is in saturation. And the output voltage will be nothing but VCE, which we have assumed as 0.2 volt. So what we have confirmed for the first case, when the input applied was 0.2 volt, the output was 5 volt, and when we applied a high output, we get a input voltage of 0.2 volt, which is across this 0.2 volt. So we can say now that when we applied 0, we got 1, and when we got applied 1, we got 0. So yeah, this BJT is acting as an inverter or a NOT gate. Is there any doubt in this question? This is an important concept which I have tried to solve quantitatively, taking certain specific values. Is there any doubt? See, these last three questions are important from the perspective of assignments. I'll try to explain briefly these last three quantitative questions because they are purely mathematical. So in this question, what we need to determine, we needed to determine V naught, and it is nothing but we assume that whatever this D1 and D2 can be. So for D1, we knew it is quite high voltage applied at the positive terminal, and for D2, it was at ground, the positive terminal. So we assumed that D1 was in forward bias and D2 is in reverse bias, and we made a circuit out of it, and we applied the KCL equation, from where we got to know that the current is positive, which proved that the assumption of taking D1 as forward and reverse bias was correct. So finally, we calculated V naught, which was a voltage drop across it, and it was nothing but 1 kilo into whatever current we got, which was 9.3 milli. So V naught was 9.3 for this case. And for the second question, we needed to determine the output level for the positive logic AND gate. So again, we assume since it is a high voltage, we assume that this D1 is off state, which is reverse bias, and this D2 is on state since we have applied the negative terminal to ground. So yeah, and from the assumption we made a circuit and then again applied a KCL. So someone has a doubt that is this 10 even? So it was not even since it is open circuit. This 10 volt was this E. So the equation was something minus 10 plus the current is in this direction plus IR into the voltage drop VD. And we solved that the current is coming positive, so the assumption was again correct. And then this voltage was, since the current is in this direction, so it was minus IR plus 10 volt. And after solving, we got the answer as 0.7 volt for this question. And yeah, this one was important, so maybe I'll try to write shortly. For cutoff, what was the condition? That VB less than 0.6. We'll directly say that the diode is in cutoff. Then for active, we'll say VB is greater than 0.6 but less than 0.7. and VC is greater than 0.8. And the condition for this is it was IB was HFE, sorry, IC was HFE into IB. I hope it is clear. I don't have much space. And for saturation, BB was even greater than 0.7 and less than 0.8, and this VC was assumed to be 0.2 volt, and the condition was this, which needs to be satisfied to get this circuit work as an inverter. And we did some mathematics, and this IB was coming out as 0.195 milli, and this ICS was coming out as 4.8 milli, and we checked that if this condition is getting satisfied, and we got to know that it is getting satisfied, and we got for 0.2 input we got a high output, and for 0.5 volt output we get a low output, which is 0.2 volt. So for a 0 we get a 1, for a 1 we get a 0. So yeah, this is working as an inverter. So is there any doubt in the whole session that we had? You can see all the questions. For the first week it was basic. There will be one more live session tomorrow. So yeah, these were the basic questions, some basic circuit questions, then some gate universal gates question, then AND gate questions, basic diode questions, noise margin, CMOS logics. This was important, and also this equation to circuit was also important concept. Okay, I guess I missed this question, that which of the following majorly determines the number of emitters. So in TTL you might have already know that all the inputs are applied. It is a multi-emitter circuit. So number of input gates that we have determines this number of emitters in the TTL. So this is nothing but fan in. Fan in is the inputs, and fan outs are the number of output that can be driven using those inputs. So yeah, this has fan in. I guess I missed this question. Sorry for that. And then we did some quantitative analysis also of the circuits. We took some bias condition and solved few diode equations. Yeah, so for this output was 9.3 volt. Then we solved the output level of this AND circuit, which was zero 0.7 volts. And then we tried to wrap it up using a concept that a BJT, how a BJT can act as an inverter. So is there any doubt in this? Please, you can ask. Maybe you can also tell how was the session. We'll wrap it up in 5 minutes. So if anyone is having any doubt, you can ask. Okay, then we shall meet in the next week for the again a live session. I hope this was good and you might have got something out of it. Thank you for attending. If you are having any doubt, you can still ask. I'll end this session in 2 minutes. Thank you, all of you. Yeah, thank you for the feedback. Okay then. I guess we can wrap it up now. Thank you for attending. It was great interacting with all of you. We shall meet in the next week. You all can leave now.